You should now have watched 2 videos on Gibbs free energy. Unfortunately, there's not a video I found that did a good attempt at doing the calculations for this or giving you a proper, fully worked calculation. So I thought I would do one. The best thing about Gibbs free energy is that instead of us having to learn this and this, like we did in the previous quick test, it combines everything into one equation. This one, which is in the data booklet. Also, please note that there's another one for Gibbs free energy, which is very similar to the one for entropy and enthalpy of formation, and you would use it exactly the same way. So they might look complicated, but these 3 are effectively one calculation. You'd be doing exactly the same things. But I'm going to have a look at this one today and to show you the hitches that people encounter when using it. Looking at this question, we have been given delta G naughts, we've been given values for delta H naught and S naughts. So that would hint that the equation that we are going to be using is this last one here, delta G naught equals delta H naught minus T delta S. So if we plot that down, delta G naught equals delta H naught minus T delta S naught. Having a look at the data that we've been given data for products and reactants from this equation. But what we haven't been given is an overall delta S naught. We've just been given individual S naughts or individual entropies for each of these things. So we're going to need to calculate delta S naught. Luckily, we've been given delta H naught, although they've given us delta H's, so they've given us delta H naught for our hydrogen as 0, our oxygen are 0. Remember that the delta H formation for each of these is 0 because they are elements in their standard state. And for this one, we've been given minus 286. So using the equation, which is delta H naught equals the sum of the delta H's of the products minus the sum of the delta H's of the reactants. This one's pretty easy because the products is minus 286 and there is nothing at all for the reactants. So our delta H is just the 286 that is shown for water in the table. However, we need our delta S naught. So using exactly the same or the very similar style of equation, we need delta S of the products minus the sum of delta S naught of the reactants. And what we've been given for our delta S naught, for our S naught, is for our hydrogen we had 131, for our oxygen was 205, and for our water was 70. Substituting that in, we have the products is 70, and then we're going to minus the sum of all our reactants. And this is the important bit for this. We've got our 131, but please note the half here which means that we've only got half of our 205 because we only have half of a mole. So simplifying all of that, we get 70 minus 102.5 minus 131, which equals minus 163.5 joules. Remember joules? Remember this one's kilojoules? That's going to become important when we substitute that in to this equation up here. So our delta G equals delta H naught minus T delta S naught. Our delta H is negative 286,000 joules, because we need to multiply this by 1,000 to convert it into joules, not kilojoules. Take away 298, which is our temperature, multiplied by minus 163.5, which equals minus 286,000 minus 48723, which works out as negative 237,277 joules per mole. This looks like an awful lot of significant figures, so having a look back at the data we've been given, a lot of them are 3 significant figures, so we'll go with that. So that would make that minus 237 joules per mole. These units can sometimes lead to a little bit of confusion, but if you actually work through what you did in this equation with the units in place, our delta G, which is what we're trying to find, was a combination of joules by the time we converted this from kilojoules. We've got Kelvin, and we've got this, our entropy is measured in joules per Kelvin per mole. Grab a book, sit down and read, darling. Okay? Can you do it fast so that I can keep going? These units can sometimes be confusing for pupils, but if we want to find out what the units are, then we have a look at what we did in this equation. Delta H was given to us as kilojoules per mole, but we converted this into joules per mole by multiplying by 1,000. We're then taking away from that 298, which was Kelvin, multiplied by the entropy, the units of which are joules per Kelvin per mole. So if we simplify all this down, we've got joules per mole taken away. This Kelvin, it cancels out this per Kelvin. This is why it's really important that you stick with your small k's for kilojoules, because you can see how this starts to turn into a nightmare. If you've got capital K's and small k's, what cancels out with what? But that then, once cancelled out, your Kelvin and per Kelvin also becomes joules per mole. So joules per mole, take away joules per mole, is joules per mole.